Thank you, Allison. Okay, hello everyone and welcome. I'm Leslie Shee from the U.S. Geological Survey. I am co-hosting this ESIP IT&I, that's Interoperability and Technology webinar. I'm co-hosting it with Allison Mills from ESIP. This webinar is a joint venture between ESIP IT&I and the USGS Community for Data Integration Tech Stack group. So welcome to those of you in those groups. The topic we have today is openEO, modern high-level API to define Earth observation processing workflows. And we are happy to welcome the presenters, Matthias Mohr from University of Muenster and Alex Jacob, right? Did I get that the right way? From Eurac Research. Okay, so welcome. Just a note that if you have questions during the presentation, please feel free to type them into the chat. We'll get to them at the end of the presentation in the order that they come in, and we should have time for that discussion after the presentation. So thank you very much, and I'll turn it over to Alex.
Great, yeah, thanks a lot for the introduction. Today, Matthias and myself will speak to you. We will give you first a little bit of an overview. Why do we think that we need openEO and what it's good for? Then we have an introduction to openEO, and then we will give you also some examples of some implementations of openEO that we have already around and that we currently work on. And then we will conclude a little bit of if any one of you is interested in how to get started with working with openEO development or anything that will come in the end. Yeah. So why do we need openEO? And then the first part is the standardization gap. So all we want to do is some kind of nice data analysis. So we want to gain some kind of information, be it from a map, from a time series or something. And of course, for this, we need data. We are in the lucky situation nowadays that we have lots of data there, a lot of satellite Earth observation data coming in all kinds of flavors, optical data, radar data, hyperspectral data, whatever. And the unfortunate thing is that there are so many different offers of how to provide this data to you that it can become quite complex. We have classic file systems in your company's network sharing system, maybe, or even your own workstation computer. You might have some sort of more complex system like a data cube that exposes the data to you, or some other cloud-based storage system like an Amazon S3 storage or something like this. And then when you do your work and you do your development in some of the common scientific programming languages like R or so, then for each of these, you need to implement a different way of accessing these. So one coding session for the data cube, one for your file system with all the paths and so on, and one for an S3 bucket to link to. And then if you have several programming environments in your organization or company or whatever, then you will have for each programming language a lot of different code snippets around for accessing all of these different ones. And you can see where this is going. This is basically growing quadratically with the amount of components that you have here. So it can be quite confusing. It requires a lot of development and also maintenance and finding this. So that's quite challenging. So that's one of the issues that we have had before. Another thing is the data management burden and organization of your workflows. There's quite a lot of repetitive things that every single researcher or data scientist need to do. Comes with the classic workflow here. An example for Sentinel-2 would work just as well for Landsat or something similar. You need to identify your study area, search for the data of interest in your area of interest, download all this stuff, then possibly you have to do still some pre-processing there. Then you need to resample that to some different resolution on which you want to work on, to some more subsetting in space and time. Finally, in point number 7 is where you start to do the actual work that you wanted to do, the kind of analysis that you want to carry out. And finally, the product packaging and delivery, creating a map or derive any other kind of visualization from the information that you want to extract. Quite often, again, also on the data management side, when you work in cloud systems, you start there with an empty shell. Basically, you get access to some kind of compute resources, a number of virtual CPUs and RAM, and maybe some disk space. And then you start to set up your virtual machine by having to install a lot of libraries and tool stack and so on. So again, a lot of time that you need to invest to set up your processing chain. And finally, once you have managed all of this part, then you still might need to work on efficiency of your processing in terms of parallelization. You want to go from something serial to something more parallelized when you go large scale. And again, this is quite a lot of work and effort, especially if you're not a system engineer and know very well how to deal with these kind of issues. Another thing is that once you have set it all up, your system that is all perfectly standardized, and you link it to a number of different cloud solutions, and you do start comparing results. This is actually a funny result that we got in the end of our original openEO project, which was a Horizon Europe, Horizon 2020 project. We realized then, okay, now we have all the standardized processing chains, everything is the same, but still the results are different, which leads to a different topic, which we will not cover today, but was still nice to see here that by being sure that all the data processing and everything was the same, we could isolate that the issues why our results were different are because of how the data has been processed. This comes back to the fit for purpose or Lanolis ready data. And how they're defined. Some of them might have applied some kind of cloud screening and thrown away images that have clouds, others not, different atmospheric correction and so on. So there are lots of issues here. The nice thing with openEO was in the end, we could at least find these issues, but there's still a long way to go in order to really standardize everything to a level that you can seamlessly work between the different clouds. Now I will hand over to Matthias, who will give you a little bit of an overview of the API itself and how it works.
Yes, hey there. Thank you, Alex, for the introductional motivational talk. So the actual solution for this that we then thought about is to specify an API between these layers, an HTTP API. And our first thought was, well, that could be a very thick layer in between that does the translating for all of them. And in the end, we realized, well, this doesn't need to be as thick, but it's a very thin layer in between that just gives an overview and really a thin thing in between. And all the big blocks that need to be implemented are actually on the client and the backend side. The API layer we will get to a little bit later, and of what it supports and what it doesn't support. It is specified with openAPI, so you can basically just use the openAPI tooling to implement clients and servers if you like. The openEO ecosystem has a couple of solutions around for backend side and client side implementations that you can reuse. We'll also get to them later on. And the API is really just the HTTP layer. The processing is done via separate specification, which are the processes from openEO, which is some kind of let's say programming language itself, which you can use to, or maybe more like a library for data processing that you can use. And everything is centered around the OGC APIs, basically. So the openEO API is using the building blocks from the OGC API in various ways. So for example, it's based on OGC API commons and also OGC API features, which are the newer variants of the OGC APIs, which beforehand were like WFS, for example. And that, of course, always leads often also to Stack, which is based on OGC API features, which is used throughout the whole API whenever data gets into play, like for the data discovery of which collections we use or how the data is exported. The processing is something that I just covered briefly. Basically, we have maybe click a bit more. So once you start with openEO, the first thing that you realize is that you get to some clients that you can use, which is R, Python, or JavaScript, or based on JavaScript. There's also a web-based tool, a UI, which you can just access in the browser. And this is all then giving you the processing capabilities around data cubes. We will get to data cubes later as well, why we use them. But all the things that you really need is all in these clients. You just need to understand which collections are available at the openEO implementation, can load them in a very aligned way through data cubes, and then specify what things to do with this data cube. And then this results in an abstract processing graph, which holds all the information about which process to run in which order, whether something can be parallelized, etc. And then you get, in the end, you send this thing to the backend infrastructure, and that executes it either via batch jobs, if it's something that is a bit more heavy, or synchronously, or via web services, so that you can directly move around, zoom in, zoom out, pan, etc. And then the execution engine processes everything around, makes the result available, and you can access it via different means through OGC APIs again, or just download it, or use a cog, or whatever is the preferred way of further working with the data. So the central unit that we have in the processing are data cubes. Traditionally, you would think more about files and image collections, etc. But that's not the case here, because all the pre-processing that you want to do or need to do if you have image collections and files, you still need to align, you need to remove overlap, etc. And that's all already solved for you if you have data cubes. You just need to really think about what data do I want, which extents do I want to have, specify that, load the data into a multidimensional array, which is usually very large with Earth observation data and other different related domains that usually doesn't fit into memory. And as such, the data cube in the back end can basically be processed in smaller units that, depending on how the processing graph is structured, can be made more smart, because the processes tell you how the data is used actually in the end. And as such, you don't run into these memory issues. You can process things in parallel, and then also process only the things you need. So if you just want to process on a single pixel, that is totally fine. You don't need to care in which file that is. You just specify, I want this pixel at this point with, I don't know, a couple of timestamps, and then process it. Or you just specify a wild, I don't know, polygon that you want to use, give that, hand over to the backend, and it loads the corresponding data without any shuffling around with files. So that can also be multidimensional, of course. So if you have 2 time dimensions, no problem. In EO, it's usually X, Y as spatial dimensions, T time dimension, and bands. But there are other things that can be in there. For example, a dimension that is consists of vector data, for example, or like as said in metrology, maybe multiple timestamps, time dimensions, for example. And then we'll get a bit more into details about the API. As I said, it's all centered around HTTP. The API communication is via JSON. It's all defined in openAPI. You can use tooling in openAPI to render the documentation, to like generate stubs for clients or servers, make validation with it, etc. And we have defined a couple of endpoints that we go through now, or capabilities. And these are the various like building blocks in openEO. So for example, the first thing is, of course, you need to discover the basic capabilities of the API and the instance that is implementing it. So / gives you all the things that you need for the first connection. That is the same basically, or very similar to what you get in OGC APIs as well. There are links included to the other endpoints. You have a well-known document available so that you can choose between different versions of an implementation. You can get information about which file formats can be used as input and output. Conformance classes are also aligned with OGC API so that you can get a feeling of what parts of the API are implemented. And then for data discovery, there is /collections for the list of collections that you can use. So like one collection could be Sentinel-2 level 2A, for example, or Landsat 8, or whatever you have. This is based on OGC APIs and Stack APIs. So it's basically the same, except for that we don't usually host individual items at that point. So that's not primarily download servers, but a service to process on the cloud. But if you want, you can add that, and then it's Stack API compliant completely. Processes basically give you all the predefined processes that a backend implements. It's a base set you're working on. This is very flexible. You can add in your implementation processes that you like. It's all schema based, and all the clients basically adopt what they get from the API and then can offer customized interfaces. You can also like use the predefined processes to define your own processes. So user-defined processes basically, store them and reuse them. So for example, if you only have math processes available, divide, addition, etc., and you want to and don't have a process specifically for NDVI, then you could, for example, define an AVI process based on the math-based processes, store it, and then reuse it in all your other workflows. So that's really a modular way to compose your smaller building blocks for building operational chains and then reuse them. Results can be processed in multiple ways. As I said before, it's either you can like smaller chunks can be processed and downloaded synchronously. So you just hit the server and it returns in a couple of seconds or minutes a result that's directly downloaded to your computer. Or if it's more work to do, then you submit them as batch jobs. And there you have additional capabilities. For example, you can estimate the runtime of the jobs. You can edit the jobs, you can like really manage things, work on metadata, get the results also in a way that it's stored continuously, so you can share them with colleagues, etc., make them available or load them into QGIS or other clients. And maybe click once more, the service at the end, yeah. And the third way to run results, run processing and work with results are the secondary web services, which is basically also give them the process that you want to do, and then it processes on the fly for, depending on like what your use case is. For example, if you have a WMTS or WMS, some kind of visualization service, and you show that on a map, it gets the information about the area that you're looking at, the zoom level, and then it only computes for that part basically. So that's basically on the fly processing for visualization purposes. So if you want to zoom in, then it computes the higher or lower zoom levels. And that can expose different ways of accessing the data in the end. So here is an entry point for other OGC services, for example. So if you want to have OGC API map, then you can implement that and add that. If you want to use or support WMS, the old traditional way, do that, or WCS or non-OGC APIs like XYZ, etc. That's all the interfaces to set these services up. and make them available for users in addition to the openEO API. So there's really a lot of reuse. You can also upload your own files so that you can reuse your data that you have, upload, I don't know, geometries that you want to reuse or machine learning models, etc., so that you can reuse them in your processing chain. Authentication is handled usually via OpenID Connect. You have some basic functionalities for managing profiles and billing in the API as well. And another thing is that you can run UDFs, so-called user-defined functions, which is a way to run custom code that is not covered by our predefined processes, which, for example, can be some kind of machine learning integration into openEO, which is not defined yet, or some other libraries that you're usually using and are not covered. Currently, that's available in Python and in R. So any library that you can use in Python and R can, in theory, also be used as code in the processing graphs. We have two extensions defined right now to the API as well, which is the order extension and the federation extension. The order extension is to request and manage commercial data or data from some kind of archive. I don't know if you have things stored still on tape archives or something like that. This can be used to order that and make them available as new collections that your users can then use in their workflows. And the federation extension is something, if you want to have multiple implementations behind a single interface, something like a proxy in front of it, then there are ways to expose that through the API as well and make the clients aware that there could be something more behind this one thing that it connects to. We will get into details there when we talk about openEO later. Yeah, the processes are defined, as I said, as schemas basically, and we all render them as nicely visualized documentation here. I think right now we have about 150 predefined processes around, which cover a lot of use cases already, but there's also ways, always ways to extend that and make available more processes for more use cases in different domains. Recently, we've also looked into, for example, climatology a bit more, meteorology as addition as for Earth observation. Yeah, the link is up there if you want to have a look what's available, and they're all centered around data cubes basically. So that's always your entry point, and then you have additional processes that you can run as part of these cube-related processes. Yeah, so a process graph basically starts like that. You have processes that are centered around the data cubes you load at the beginning. For example, this is a visualization from the web UI. For example, to different data sets, collections here, Sentinel-1, and well, you just load Sentinel-1 twice, I guess with different extents. Then you can do some processing, merging them, for example, data fusion, reduce dimensions, and do different things with them. And these processes, for example, the reduced dimension processes, then if you like reduce the dimension, you need to do some computations to make multiple values into one. Then you can, for example, work on formulas in the web editor. You can have like an easy way to just input a formula, or in the clients, you just use the native mathematical operations that you have in R or Python, and that gets translated into the processing graph in the end, which then looks a bit weird and complex, but in the end, it's translatable from the clients, and you don't need to really worry about that, which is then executed as part of the reduce process in parallel over all the parts of the data cube that can be chunked here. We have different clients. One is the Python client. So the code looks like that. In all clients, it looks very similar. For example, you have you're usually connecting and logging in, and then you specify which collection to load. You can make limitations to the data cube that is loaded by spatial and temporal extent, and load different bands. Also filter on the metadata. And then you run different data cube related processes. Apply is one of the common ones that you use, or reduce dimension, apply dimension, which are all the normal data cube processes. Save the result in the end, send it to the back end, and start it for processing. And that works the same across all the clients basically. And then you get your result, can use it either locally or further store it on the back end and process it in another job. This looks very similar in the openEO R client. We also have integration into RStudio there. For the Python client, there is integration into Jupyter Labs, for example, so that if you run the processes, then you get different kinds of visualizations directly into the Jupyter Lab, nicely rendered. And yeah, you have basically the same steps all the time. You connect to a backend. You can discover the processes or collections. Then load the data again, and you see it looks very similar. You have the load collection process, you have specify spatial and temporal extents. And by that, you get the same process graph in the background that you can send to multiple backends. So that's really the beauty. You can translate basically between the different programming languages. You can switch between backends. You can run the same processing graph, basically, for example, on Google Earth Engine or on Vito or on some kind of other infrastructure that you're running, and they all give you basically the same results in the end. That is the UI that we have in the browser that you can use. It's not for code, like you don't need to know coding for this. Then you get these nice models here that you can construct by drag and drop and connect them and modify the parameters. Manage the batch jobs, look into your logging like logs that you get back. You can visualize the results on the right side on a map. You can make charts, etc. And basically go through all the things nicely if you don't want to code, basically.
Great. Yeah.
Yeah.
I don't know.
I hand over again.
If you want to, sorry, I didn't want to cut you. What was that?
No, that's fine.
Okay. So this was the overview of all the different clients. Yeah, I guess the key message is really we try to find something for every flavor. Maybe very important to note also is that we have created these as standardized packages. So in R, this is an official CRAN package, which you can easily install. The same for Python, it's installable via pip. So you don't need to do any kind of cloning from a custom Git repository. They're all available through standard channels now.
I'll put the links in the chat.
Yeah, great. Thanks, Matthias. So just a quick overview of a use case that we started to work on the original openEO project a few years back. But this is a use case where we wanted to do the mapping of wet snow in order to understand melting processes in mountain areas for runoff prediction, for example. In this case, first thing that openEO can do for us is exactly access these data sets, or a collection of, in this case, Sentinel-1 SAR data intensities, and then we had derived from MODIS also snow cover maps. Then we can use the functions like merge cubes to bring them into the same gridding that we want, and then continue to work on these. We can do some processing in our workflow that we need to do here. For example, for finding areas that are wet, we need to generate a kind of reference SAR image and subtract every single image from that to see basically an anomaly of a standard state, and that would be the wet state in this case. And then these are basically just simple mathematical functions similar to what Matthias has shown in the client examples there. Then we have some kind of classification algorithm that is not standard defined yet in openEO. So for this, we can use a specialized function, a so-called user-defined function, where we can do an actual code ingestion into our processing chain in the programming languages of either R or Python. The funny thing is, since these are two different environments, then we can even do the standard part of the processing in Python and the UDF in R, or vice versa. All of this we can mix and match here. Again, always possible because we have this abstraction layer of the process graph that Matthias has presented earlier. In this case, the UDF is fairly simple, so there's just some thresholding on some of the values in order to define the different classes of wet snow, dry snow, and no snow. And then finally, again, with standard openEO processes, we can download our results. This will be a time series over a season, over a full melting season, and then we get our nicely animated series here, where you can see the onset of the melting towards spring. So the further we go into spring, the more blue you see because of more melting processing here. Just to give a quick example, this is just a list of currently existing openEO implementations. So we are not the only ones anymore. We, as the inventors or first developers of this, who use this. This has been found some level of adoption so far, mainly in Europe, because that's where the original funding and the original organizations of development have come from. But now also with events like this, we try to make this a little bit wider known, and really hope that's also interesting for you. We have companies like EGOS or EODC who have implemented this, research institutes like Eurac, RISE, or the University of Muenster from Matthias who have this. We have done also some playing around with building a backend of openEO on top of Google Earth engines to connect to some of the commercial available services. Now there's an organization in Sweden who sets up openEO as an official data channel for all kinds of government organizations so that they can access all the remote sensing data that they have over Sweden in a standardized and concise and easy way. There are also commercial platforms like the Sentinel Hub or the openEO platform, which I will introduce to you now also. With this, we come to the next concept. So this is everything we've shown so far is what happens inside one of these backends. Most recently, in a project together with the European Space Agency, we are working on a federation of backends. So so far we had just the API, and then you connect to one of these examples, different types of things. Now with openEO platform, we have a lot of different backends and data services, and all of them we want to link and make the transition between them as seamless as possible. For this, we invented a new component that you can put in front, which is the openEO platform aggregator. This is exactly this element which allows a number of openEO backends to act as a federation and do things like common a common data catalog, so that you can see in one list the data offerings of all members of the federation. The same goes for the processing facilities. It will also do smart selections for you. If you select a data set that is only available in EODC and you send your process graph, it will automatically only send that here, not to others who cannot support this kind of processing. So really makes it even more seamless to work between different environments. There's also another level of simplification, which is a single sign-on through the EGI check-in, which is also based on OpenID Connect as the standard openEO authorization and authentication mechanisms. And on top of this, for this specific federation, the openEO platform, there are also offerings that support research entities to get credits here, so you can get sponsoring, so that you don't have to pay for a commercial offer, but you can get sponsoring through ESA or the European Open Science Cloud to run your processing there. Now the federation allows us to do a number of nice things. Apart from making it easier to work in different backends, you can also utilize the full potential by for example, uniting the processing power of 3 processing centers to tackle very large jobs. For example, we did most recently a crop map of all the countries in Europe. This was an area covering around 5,000 MGRS tiles. So that's quite extensive amount of data, and by combining and sending these jobs to the different backends in parallel, we were able to complete this in relatively short time. I think we can do this in just a week or so if we need to now. Another example is where you have data sets and capabilities that are unique to some of the backends, and then you can also start to work in a federated processing approach where parts of your graph will be executed in one backend, intermediate results shipped to another, and then the processing continues there. We had an example there for doing forest canopy mapping over the European Alps. What we started doing is finding interesting areas for training a model to understand canopy cover from high resolution data. We used Planet Labs data here for this example. This Planet data, however, was only available through commercial services and through a specific backend, and that in our case was the Sentinel Hub, who has an arrangement with Planet so that they can offer the commercial data there. So we had to do all of the pre-processing that was linked to training our model with high resolution data inside a facility that can be linked there. So the first thing we did was this study area selection in-house in Europe. Then we shipped this list of polygons to one of the backends. This goes also back to what Matthias showed with the upload of your own data. So we had our list of study areas, which were used then to do an order of the Planet data and then do some processing with the ordered data that we got there as a private collection. In the end, from all of this, what we get are polygons for which we know what the canopy cover is. This is our reference data. These polygons are just very small vector data. So in the end, for our 150 test areas for train our machine learning model here, we only had to transfer something like 5 megabytes of data, even though we worked with a data set. So that the Planet data that was behind this was something like 50 to 100 gigabytes, so much larger than the actual data set that we needed to ship after processing. And then finally, we wanted to train. We have used this for a regression model and apply it with Sentinel-2 data, which we had the full collection available and pre-processed in a specific way in a different data center, in this case, the EODC. And then we could basically train and predict our model here. And in this way, we were working actually in 3 different backend locations plus our own environment. So basically 4 different environments where this processing has been touched. And that's exactly the kind of complex federated processing that we are currently working on. This is not yet fully operational, but the proof of concept are there, and first results like this one could be achieved now with this. On the note of federation, we're also currently working on the extension of this federation. So there had been 3 providers so far, a 4th is coming. And then we also work on a different type of federation by including different types of data. So far, most of the processing in openEO has been based on raster or gridded data. We are now also adding a data provider which works with vector databases, and we are currently exploring the concept of vector data cubes and how to link those into our processing chains. It's quite relevant for features for machine learning algorithms, for example, and also other types of environments which are like hosted Jupyter environments and so on, to easily link on top of openEO platform. Now I will give you just a quick example of a very small backend, the one that we use here in-house in Eurac, just to show you the benefits even for just small scale operations. Our own cluster that we host here in Eurac is just a standard research cluster with in the few hundreds number of cores and then the few terabytes of RAM. So nothing fancy in modern cloud and petascale computing, but fine for most of our needs in EO. What is typical for us is that we do some kind of pre-processing with the data that we get. That might be the classic radar pre-processing that is needed in order to derive all kinds of products that are used with radar data or optical data, and this we then organize in data cubes. For this, for historic reasons and different management practices, we have actually 2 different systems. One is Rasterman, which is a commercial data cube software, and then we also use the Open Data Cube. All of these are basically index databases that give a data cube view on the actual data that is stored on disk. from here on, we have our data queues with which we can interact with openEO. This already made life for me as one who's responsible also for data management in our institution more easy, because now with openEO I could actually have different data cube softwares exposed through one API, so that for our researchers and users in our environment, it doesn't matter anymore to need to know if the data is stored on disk or in Rasterman or an open data cube. They just get openEO and find the type of collection that they want and load it, and don't care about anything that is happening on the right hand side here, basically. And the other thing which is nice for me is that I can support different clients and programming languages. We have quite a lot of researchers coming from different universities. Some of them are used to work in Python, some of them are used to work in R. With openEO, I don't need to have different processing environments in the back end. The clients can be in different languages and then create their workflows, and in the end, how this is processed on this side doesn't matter for this side, again through this abstraction layer of the process graph that we have. And in this way we can easily support also a multitude of different client environments for the researchers to work in. Plus, of course, the ability to add user-defined functions. In research, there are always new things that we have not yet seen. We come up with new ideas for algorithms and workflows. Before they become a standardized process in openEO, there's a phase where people experiment, and then it's nice to have the user-defined functions around to test new things which are not based on the predefined processes. Nevertheless, one should use the predefined processes as much as possible, because these are the ones that allow a backend to optimize processing and make it really scalable and fast. When someone writes their own code, you never know how they write it, into what level of expertise. So this might not be as efficient to execute as predefined processes. In our case, actually, the main processing engine is based on Xarray as in Python, and as a data struct. And then we use Dask for parallelization there in order to run it smoothly on many cores and scalable. With Dask, we can also dynamically scale up based on the number of workers that we want to have, and that's a great way of parallelizing the processing here. But again, whatever happens here, I can even change this and have a different implementation at a later point. The end user will never see this, which is a great flexibility for us. So openEO in this case is really the method to create this. What does the user actually want to do, and generates this abstract graph. The open data cube is the virtual data cube layer, so to say, that helps us to generate indices over any kind of data set coming either from an S3 storage or a network drive, then expose this as a collection with all the stack metadata, which enables it then to run the openEO processes on top of it. In the backend, we have all the different processes, the reference implementations done based on Xarray and Dask, so that then we can easily scale out the processing there. Again, this allows us also that it's really only processed what is actually needed. Xarray and Dask are all working with lazy loading, so you will always only process the pixels that are actually touched upon and want to be worked on by your user, which is quite good. Okay, finally, getting started with openEO, some useful links. So this is just an overview for you. It's really important to stress again that all of what we do in openEO is actually also open source. So we try really to be as open as possible with everything that we do. Most of these repositories, as you can see, are under the Apache 2.0 license, so you can basically do whatever you want with that, and we really make it available to everyone. There are a lot of different implementations out there for different backends, like the one that I've presented you in Eurac, which is the WCPS driver. But there are also other backends working on completely different software stacks. There's, for example, one working on GeoTrellis, and behind this is actually a Spark cluster. So it's a very complete different backend infrastructure. These two work together to generate the backend that Vito has, for example. There's EODC, which also works on the X-array and Dask cluster, and we are currently working on a way of harmonizing the development of the processes there so that the process part can be shared between different backends again. What is important here is if you want to set up openEO yourself, then first have a look at what's already there and on what kind of software stacks and tooling this is built. If you have any questions there, you can also come to us. We can guide you a little bit because can be quite intimidating. I think by now when you go on GitHub openEO, there are something like 50 or so repositories under the GitHub group because of all the different development. So you can also contact Matthias or me for reference, for helping you there to find your way. As Matthias already said, all of this is based, even the standard on which the API is generated is an open standard, which means there comes a lot of tooling around this that helps you to get started quickly if you want to start from scratch by generating stubs for both client and server-side library parts so that you can quickly get your RESTful API up. And then, of course, divide and conquer, start with the most essential endpoints first before you tackle the less essential. So the most essential, of course, is the finding the data and doing the processing. So the collection stuff and the job stuff, basically, and then everything else, authentication, user-defined functions, user data, and so on, that comes at a later stage if you want to do your own development. So in general, as a conclusion, all of this is human and machine readable, basically based on JSON for all the information that's sent around between clients and servers. Basically, apart from the data sets, of course, they come then in whatever data format you asked for. The API itself is HTTP based. There's a large catalog of predefined processes and reference implementations in different backends for those already. These can be extended by user-defined functions when what you want to achieve is not feasible with what has already been defined. There is the whole concept of the process graph as an abstraction layer that really helps you to isolate the client-side problems from the server-side problems, which from data center operations part is really nice. There are a lot of reference implementations for both sides, the client side and the server side already there. So we have 3 different clients already, Python, R, and JavaScript. But for example, if for some reason you need to have a different programming language, like, I don't know, Julia, Scala, or whatever is fancy now, then you could also easily develop a client for this without changing anything on the backend side now. It was from the beginning meant to be integrable with existing hard and software infrastructure. And all the existing backend can be used also as a starting point for your own implementation. You will also find when looking at our website that there's quite extensive documentation and guides around for both getting started as a user, getting started as a backend developer, and everything is really open source again. Now for the future output, we continue our development of the federation concept for a more large-scale integration of different backends, more complex concepts like the vector data cubes and how to deal with this then in our standardized processing framework, different machine learning implementations. We have already started with some more simple models like random forest and a few regression models, but we want to also extend this further into deep learning and other application, machine learning application there. We are still and have from the start tried to be as much as possible aligned with OGC. When we started our development, then OGC API was not yet a thing. But then Matthias and myself from the beginning were always in touch with OGC also and participated in many of the API related hackathon events to always have a good overview of what's going on in the OGC. We're actually also both members of the OGC with our organization, so we're quite well linked there. Now there are further deployments planned. Right now we are in discussion there also with Microsoft and the planetary computer as one of the possible ones. We're looking into deeper collaboration with Pangeo also, as some of the backend software stack is actually basically like a Pangeo software stack. So we are really looking forward to integrate with them. On the note of this, next week we will give another webinar actually in I think next week's Thursday, right, Matthias? No, Wednesday. With the Pangeo community meeting to talk a little bit more on how to link and collaborate with them. We're also working on very small scale processing environments for testing and prototype development, so that you can do local processing in your own environment in Python right now, so that you don't always need to connect to a cloud service, but also can do this on a workstation or a laptop computer for just testing and setting up your workflows, small scale. And for the same reason, to also get others easier and quicker started, we are working on a small, easy to run and self-contained Docker mini backend environment, so that you can quickly have something to test against and work with. So yeah, now we are at the end of our presentation, and hopefully didn't completely overwhelm you with all this information, and happy to take your questions.
That's great, because there's a lot of questions, but first of all, thank you very much. And give you a thank you. I don't know how to do the Zoom clapping. I always do the team clapping, but thanks for that great presentation.
Okay, somebody found the clap, thanks.
Yes, and all of the links, we do have a list of questions which we'll just get started on, and maybe we'll see if we can continue the discussion in a Slack channel or something like that. But if you didn't type your question in and you have one, please don't feel intimidated by the list of questions. We'll just collect all the questions and try to make sure everyone gets some sort of answer. And this is funny because I now, even with my glasses, cannot really read these things. I'm going to scroll up to the top. So the first thing, thank you. But I'll start with the first question from me. Ryan, we'll move to some of your questions and see if we can move around with different question askers. Okay, so first, do you have an idea of the relative use of the three clients, Python, R, browser, and does that affect any of your development decisions?
What do you mean by relative use?
Just like if one is much, like, do you have much more Python users versus R and the browser?
Yeah. So Python is, I think, the most used one, followed by R. It depends a bit on the community that you're looking at. Like when you're having a lot of scientists around, then R is a bit more popular. But otherwise, it's a lot of Python. And the JavaScript client right now is mostly used for the implementation of the web editor. That is used mostly as an addition by also R and Python users, because it's a very easy way to communicate and manage stuff. So yeah, that's it mostly.
Okay, thank you. Yeah, we're going to do like a quick fire answer. So feel free to just say there's more to say, but I know there's a lot of questions. Ryan, are you interested in unmuting to choose the first question you would like to ask? Otherwise, I would just go from the top, but you can choose the most pressing question you have.
Yeah, thanks. I have way too many questions. So maybe, the big one for me is, I just want to be clear, like, so what you're doing is building a process framework for maybe schematic interop. Do you get into any, semantic interop support? I know you use Stack. It seems like you're using that as your reference model to communicate between process tasks. But is that it? Am I getting that right? Is there any way to say, link a process that generates some data to like a social science decision, that I might want to define and then track and trace?
We are not yet on that level. I think right now we're more on the really like algorithm description part with the graph. I had a very similar question from a colleague of mine recently who also wanted to go more on the semantic level, so that you can define your queries like just find me all the images where there's water kind of query and then work in this direction. I think this would need an additional library or so to deal with the semantic part and translate that into the processing workflow. And possibly also on the data set side, you need to have some kind of annotated data to be able to work with the semantics as well. So that these are two layers, which I guess would make a very interesting research and development project where we have not yet come around to work on really, but very good point for sure. And also for the future, interesting.
Great. Yeah, thanks. That was my big question. And I'm, I'm just gonna let other people ask questions, but I will email you guys as suggested. We're building a semantic interop framework at NOAA, but in some community meetings over the past year, we're going to need to interop with systems like ESA is building. So it'll be important to keep tabs. So thank you.
Sure.
Thanks, Ryan. And thanks. I would say even if you email, once you get those answers, it'd be great to share those answers on one of the ESIP Slack channels.
I
so
will
more
share.
people can
I will
see
share.
it. Okay, great. And Allison, is it okay to keep moving down some questions now? Okay, I see a couple +1s for the question. Okay, there's two, they're tied +1s, but moving in time. So you mentioned official data channel for government organizations and a little bit of collaboration there between government organizations. And we have a number of government employees on this call that might be interested in a little bit about how that got started and how they got that working. If you have any other details about that.
Well, they did exactly what we recommended. They contacted us and wanted to get to know how they can get started. And we tried to discuss with them a little bit what kind of technologies might be interesting for them. And that depends a lot, also a little bit on what's your hardware infrastructure, how do you have your data stored and so on. In the end, they went with an implementation that was similar but to the one that we have at Eurac, so the one based on an X-ray and task for scalability, but they did a lot of own development also, since they had also basically a lot more funding than we ever had for creating our proof of concept backend, basically, to optimize that. I know Matthias probably has the latest on how it's going there.
Yeah, going well. Still on X-ray task. Yeah,
Okay,
it's public, I think, as well. If someone is interested, I think we can connect you to them as well.
This was RISE, the research initiative of Sweden. Yes.
Okay, thank you. Maybe we'll follow up to learn a bit more. It's always great to see those connections being made. Sometimes it's hard to get the different organizations to collaborate. Okay, and if I may, I will go on to at least one more. I see, let's see, there's also a second hand up about so you mentioned a lot of different federated pieces that are aligned here. And I can imagine it is challenging to keep everyone kind of all up to date as the project moves forward. Like one piece might do an update that affects other pieces. Could you talk a bit about how you keep all these pieces informed and working together?
Yeah, so there are different pieces that change over time. That is, at one hand, of course, the API itself, which is very slow moving and usually changing in a way that it's not breaking anything. So that is not really an issue here. At least it hasn't been in the past. And the other thing that is, I think, more likely to break if you change things is the processing definitions, basically. But there, it is in a way done that the process itself exposes them as schemas, basically, so the clients can adopt to that. So whenever a backend uses a bit older schema, the clients understands it and can offer still a good way to work with it without like breaking anything. Of course, in the long run, that decreases the interoperability between backends. So if you want to send the same process to another backend, you may run into issues then. But working with it on a single backend basically is not an issue because the clients are adaptive to that change. But yeah, I mean, over time, that follows along, and implementations usually keep up again. But the smaller changes in between that are there or might be there over time are not a big issue in the end.
But we, of course, as an open source project, we have this project steering committee also, where we have monthly meetings and also developer meetings, so where everyone can participate, so that we try to keep everyone in the loop. And if somebody brings in ideas that are really breaking, then we bring them to this council for voting and decisions, so that all the ones that are interactive with us and the open source development get the chance to decide on that together, basically.
Great, thanks for mentioning it. Takes meeting that type of connection time to keep it aligned. Okay, I'm going to turn it back over to Allison because we are at the end of the hour. Thank you again for the presentation and the questions that we hope to follow up on and see the discussion. So Allison.
Yeah, thank you, everyone. Let's give another virtual round of applause for Alex and Matthias. And so we will follow up. We've been recording the session today, so we will have this on the YouTube IT&I playlist. It will also be up on the IT&I webpage, and it'll be going out in next week's ESIP update. So make sure to follow up on any of those questions that you want to. And it sounds like we need part 2, honestly. So stay tuned.
Well, you had to present us also with a lot of other working groups, so we can maybe find an opportunity to continue this. Thanks a lot also for having us. It was great, and happy to see that you're so engaged and interested in the topic.
Yes.
Thank you.
Thanks, folks.
Bye-bye.